superintelligence, and I believe AI would soon take over the world. How many of you believe superintelligence will happen someday? All right, great. So, good morning. My name is Jason, and I think I've already been introduced. But I still do kind of do software, but my main stronghold is more on reinforcement learning and deep learning. At the University of Ghana, I have worked with a professor on computer vision tasks and building custom models for surveillance security. But a few months ago, I took the challenge of developing, like venturing into reinforcement learning because I really loved the way the human mind works. Looking at the human brain, how the neural networks are modeled. So it's more like a framework. Every neuron, every synapse is a framework. It's a pathway where information flows and then to perceive a certain task. So today, I want to take you through, not technically, but more of how the human mind works. What is reinforcement learning and why is it very important? For example, there were some technical issues just a few seconds ago. And I obviously was not prepared for that, but some way, somehow, I learned to fix the problem. That is a direct example of exactly what reinforcement learning is. Another example is that we have a child, and the child learns to walk. So it makes mistakes, it falls down many times, but later on, it begins to know that in a particular position, it can balance itself out and then walk properly. So this is how human beings are modeled. Our brains use the only way we can explain how the human mind works, how our reasoning works, and how we pretty much think our whole lives is pretty much through reinforcement learning. Now, reinforcement learning, if I would tell, is that machine learning. How many of you have heard? I mean, you've heard of machine learning, right? Great. So, machine learning has three paradigms: supervised learning, unsupervised learning, and reinforcement learning. Supervised learning is using labeled data. So the data has already been labeled and the neural network has some examples. So when tested on new data, it's able to pretty much know well. For unsupervised learning, that data is not really labeled. So there's a lot of sparsity in the data and the neural network learns from less examples to create new insights. Now you have reinforcement learning. Reinforcement learning is very important and I think is the most powerful field in machine learning, whereby the agent, in this case, has zero examples, has never been trained before, but is able to learn and make better decisions through trial and error. The goal of reinforcement learning is to allow an agent to make the best moves possible towards a specific goal with the little mistakes. And this can be done in three ways. There are five main components to reinforcement learning. You have the agent, which is the one performing the action. So imagine I am walking around this stage, and my goal is to make it from here to the end of that chair. I am the agent. This is my environment. And the steps I take towards that goal are my actions. Now, actions come in two forms. They could be a positive action or a negative action. So with every right action I take, there is a reward. Similar to giving your child a treat for every right thing he does or she does. For every wrong action, there's a penalty. So if your child is probably being stubborn, you would definitely probably not beat the child or something like that, some sort of punishment for them to learn. That concept applies to reinforcement learning. Then there's your state. The state is the position at which I am in vis-a-vis my end goal. So the closer I am, that's the goal that we want our agents to make. Then there's reward. The reward is either a penalty or a positive reward. So now, the feedback loop is more of a dual scenario, whereby we have the agent walking towards the goal, and if I see the agent is an object, it should know that it cannot go through the object, otherwise it might fall or something might break. So it has to learn how to navigate the object, going through until it reaches its goal. This is the exact concept of reinforcement learning. Now, This is very typical, especially with self-driving cars, the Tesla. So the Tesla is fitted with sensors and cameras where it can perceive a three-dimensional space, its environment, and it knows how to stay on the side of the road, the lane. It can detect a pedestrian. It can detect other objects for it not to collide. This is all reinforcement learning, coupled with computer vision as well. Now, how does reinforcement learning work? I've already given the example of a child, the car, the Tesla as well, and I'll just give one more. I'll speak on the feedback loop between actions. So, with every action the agent makes is to maximize the throughput for it to reach its goal successfully. Sometimes the agent will reach its goal. It may take very good steps, but it may take a very long route, and we don't want that. So that is where we kind of fit an optimization algorithm in to allow the agent. And a typical example is the Monte Carlo tree search. So the Monte Carlo tree search is an algorithm that allows the agents to pretty much make decisions and find the optimal path to its destination. So I just want to play a video for you. I'm kind of skipping through the slides a bit, but I have a very interesting framework to show you at the end that I built. So this is from OpenAI, where they built a multi-agent hide and seek game, and it's a very, very powerful thing. I think we might get some audio on this. I'm not sure. I'm not sure if you get audio. But here we have two agents. So the red ones are the seekers and the blue ones are the hiders. So these were trained over millions of games, and the goal is obviously the same game of hide and seek, but they learn through what we call self-play. So they learned, they have very few examples, so they have no explicit training or knowledge of how the hiding game seek works. They just play millions and millions of times against themselves, and they realize that, oh, we can actually lock these boxes so the seeker cannot get in. So after many, many rounds, the seekers, the hiders are very, very good at what they do. But then the seekers realize they can take that and jump over the fence. So they've learned. And thus the hiders realize that, okay, now we have to take away their main sort of defense. So it looks like here they've definitely won. But the environment changes. The more complex the environment, the more the agents have to reason because they've never been in that before. So they have to know, in past games, I have pretty much had this success, but this is now open field. How do I adapt? How do I move? So lock-in boxes is one thing, and obviously they cannot be found in this moment. But the game goes on and on and on. And now the seekers realize that even though they cannot find them, they can serve the boxes, right? So it climbs the box and realize that it doesn't always have to push the box. It can climb the box and then go to its target, and voila, they've been caught. So this game goes on and on and on, and millions and millions of rounds were played. The underlying framework, I believe, was for one of the games that they played. Dota is kind of like I think an RPG, role-playing game, and it was using just a single layer LSTM neural network that was able to capture all the decisions and everything that the agent had learned and become more successful. So these are all unique games that the agent played against itself to become better at what it did. So a very fun part. You can definitely get environments like this with OpenAI Gymnasium, and it's really, really, really fun. Okay. Now, real-world applications of reinforcement learning. We have gaming, finances, real-life threats, and the fraud detection. There's also robotics as well. Factories. I mean, the AWS and factories pretty much need with robots everywhere. That's a typical example of reinforcement learning. And Tesla cars as well, the self-driving cars. Now, how do we kind of get started with reinforcement learning? So for me, I'm not your typical person that, let's say, went to school. By the way, I've done a lot of interesting things, but none of these is what I learned in school. By the way, I dropped out of college because I realized that the education system was just not my thing. And one interesting framework I like to use, I know Jesse spoke about, he used TensorFlow. TensorFlow is very easy for beginners, but PyTorch is very, very important. Personally, I think it's the most robust AI framework out there because Google themselves are replacing TensorFlow with JAX and Flags. PyTorch is like me. I mean, I'm using Windows now because Kali Linux failed on me, but I've used Linux for the past 6 years of my life, and Linux gives me extreme control over whatever I am doing. The same as PyTorch. So PyTorch allows you to create a lot of custom environments, a lot of custom agents. It gives you a lot of control. It's like this. TensorFlow, if I would say, is like a 50-piece puzzle. You cannot read, you can just do so much and it's very easy. But TensorFlow, PyTorch is like 100,000-piece puzzle. It gives you control over many, many elements. And I think the learning curve, learning it the right way, would actually be much more beneficial in the long run. It's very flexible, it's dynamic, and you can create custom environments. I've spoken about that, and also create differentiation calculations. Most of this abstract mathematics is pretty much done for you, right? But you can also extend that and create your own. So now, building agents. I was having a very interesting conversation with some of the speakers, and last night, and I told them that we build things with different frameworks and stuff. And then I was like, you know what? They were talking about the crazy things that people have done in their lives. This guy did this. Somebody built a UI interface with C#, with C. And I'm like, wow, that's interesting. So I got bored. I felt like I couldn't do anything. And I told her, you know what I did one day? I built an entire neural network in assembly. And you're like, wow, that's crazy. So one thing that I really love, math may not be a stronghold, I'll be honest, was never my stronghold. But once I'm able to apply and appreciate where I am putting the math, it really makes a whole lot of sense. And NumPy is the way to do it. I build in fact, all my reinforcement learning algorithms, agents in literally pure math using NumPy. So it allows you to have access to raw, very powerful mathematical computations and control over the mechanics of how the environment works with simulations. And it's pretty much user-friendly. Now, I want to introduce you to reinforced meta-learning. Now, we've all heard about AGI, superintelligence. And my mentor, Ilya Sutskever, former chief scientist at OpenAI. I really love his work, the creator of the GPT models and all the crazy things that we've seen today. Currently, he has his company in Tel Aviv and San Francisco called Safe Superintelligence Inc., where they're working on creating advanced superintelligence that is safe. So I was listening to one of his presentations, and he was talking about self-play. What is self-play? Self-play is when an agent plays against itself. So, for example, you're playing a chess game, but then you are not playing with someone, you're playing pretty much against yourself. Or, let's say you've been playing with a computer. At this point, you're learning all the techniques, every single thing that you could probably not know, reading online or checking everything out for you to be better. Then he spoke about HER, HER. HER stands for Hindsight Experience Replay. So with Hindsight Experience Replay, it's basically looking at everything that you have learned in the past and making your current decision based on that judgment. So I have walked up and down stairs millions of times in my life. So obviously coming up the stairs, I'm not sure fall. That's Hindsight Experience Replay. But human beings are not always in that situation. There are times where humans we'll be in a situation whereby we have never been trained for it before. We have no idea what's going on. But then, in our reasoning, we begin to simulate. If I take this action, what is the consequence of this action? If I take that action as well, what are the other consequences? So it's like a tree that explodes in many, many possibilities. Looking at that, I realized that reinforcement learning is an extremely powerful tool. But for years and years, scientists were doing it the wrong way. If we can get these agents to reason, simulate, forecast, and predict at an unprecedented accurate level, I think we're going to have one of the most powerful systems the world has ever seen. This is not about building, LLMs or large neural networks. This is the raw, fundamental foundation of what reinforcement learning is. So let me just open this quickly. And this is pretty much a project, my research work. And reinforcement learning here, the agent, this is the environment, a very, very simple environment. And in fact, this is the entire environment. It's a 5 by 5 grid. So these are the zeros, and that's 5 by 5. The goal, where the cursor is currently blinking, that's the starting point for the agent. The asterisk is the agent, right? So the agent is currently here, and the G is the end goal. Very simple. It's supposed to make it from that point to the end goal. So obviously there are many parts that it can play. If it starts from here, just probably go skip to this one, go down here, go here, go here, till it reaches the end goal. So this is not a deep reinforcement learning, meaning it has no brain in itself. It's just a raw algorithm that I have created to allow the agent to simulate things. Now, there are many things that influence this agent. Like in general, agents in general, you can decide that, oh, okay, I want to let the agent know that this is the 5 by 5 grid, this is world, it should not go out there, different things. There's so many rules. But I only added 3 rules. Number 1 was a reward for every correct move. The second one was the penalty. And the penalty was in 2 steps. Step A is for every wrong move, and step B was a greater penalty when it ended up outside its environment. And the third is pretty much the actions it can take, up, down, left, right. Those are the only 3 things. So here, as we can see, all these things you see right here are the steps. This is what the agent is thinking. If I take this particular move, where am I going to end up? If I take this move, where will I end up? So it's more like a tree node. And it's thinking, and it's extremely fast. Pretty much 0.001 seconds, because I took into consideration that the complexity of these calculations can increase in scale. And looking at the scaling law of large language models, where you have the large amount of data versus the large compute leads to more intelligent models. But I believe here, if we can design agents to think at a very high speed, very efficient, in the less amount of time, we can definitely get things going quickly. So yeah, it made it from the beginning. It made it from the beginning here, all the way to the end goal, pretty much. So yeah, it reached the end goal in 0.4 seconds for 10 steps. That was great. So I kept running this thing over and over and over again. And mind you, every time I run, it's not like it remembers its past, the past actions, like runs that it made. Everything is a new start. But something went wrong. When one day, I kept running the agent, and I realized, because the optimal steps it should take, the best scenario is 6 steps to this goal. One day, the agents made it to the end goal in 3 steps. And I was like, what's going on? Upon investigation, some way, somehow, the agent knew that it can make it to its destination faster if it skipped squares. So it went from the first top left where it started, it skipped all the way to here, and then here, and finally it made it to its goal. There was no rule, no influence to tell the agent this hack. The agent knew
some way, somehow, that it could make it there faster. How did it know? It's through its forecasting ability. So instead of hindsight, we have foresight. The agent simulated and was able to make that very massive prediction. Think about this. The agent can look, if this algorithm, which I believe the paper will come out soon, I was supposed to present this at NeurIPS, but unfortunately I missed the deadline. But agent, if our system is involved with this system, with this algorithm, we can be able to predict things before they happen. We can be able to predict floods even at a better scale, because this is not just a framework, it's an entire optimization algorithm. And then we can be able to, probably in the eyes of Elon Musk, make humans a multi-planetary species. This is what I believe. I believe we can predict so many things, we can cure diseases, we can do a lot of things, because now we have an agent. The mind of superintelligence can actually perceive the entire future. And not only that, it can prevent the worst from happening. So this is just about it, and I would proceed to maybe take a couple of questions. I think I'll just end here. Yeah, thank you.